let's start. Oh, have we started? We're going to complete our little lesson on rotational kinematics. I didn't complete it yesterday because I just went too slow. So please look at your little sheet of paper. And do you see where it says, just as we have four kinematics equations for linear motion when the blank is constant, what is constant for those four kinematic equations? What has to be constant in order to use those four kinematic equations? Yes, Logan?
Wait, no, I don't know.
Well, go ahead and guess anyway.
Velocity.
No, keep guessing. What do you say, Giancarlo?
Acceleration.
Yeah, acceleration. So you're close. But yeah, those four kinematic equations only work for constant acceleration. So we don't get to use those four kinematic equations for, let's say, circular motion. In fact, that's why acceleration has to be v squared over r, and, because we can't use the kinematic equations. Well, we have four analogous rotational kinematics equations when what do you suppose has to be constant in order for us to use these four analogous rotational kinematic equations? Yes, Fatima? Yeah, angular acceleration, yeah. So now angular acceleration has to be constant. And let me just tell you, we've got analogous equations just in linear land, okay? You know how we have displacement, velocity, acceleration, and time? In rotation land, the analog to linear displacement is angular displacement. The analog to linear velocity is angular velocity. Then you got angular acceleration. And the analog to time in linear land is also time in rotation land. That doesn't change. And so given those relationships, remember our four kinematic equations, v equals at plus v naught, and x equals 1/2 v naught plus v times t, which is another way of saying x equals just average velocity times time. They're the same thing. And they got x equals 1/2 at squared plus v naught t, or v squared equals v naught squared plus 2ax. Well, just as we have these equations in linear land, we have the same equations in rotation land. Only now it's going to be omega equals alpha t plus omega naught. And theta equals 1/2 omega naught plus omega times t, or theta equals 1/2 alpha t squared plus omega naught t, or omega squared equals omega naught squared plus 2 alpha theta, right? And I find when I have to use rotational kinematic equations, I kind of convert them into the linear and remember which linear equation to use. Then I convert back to rotation. I do that all in my head. But still, our process for doing these problems is all going to be the same. So like, hey, let's look at example number 5 on your sheet. They tell me a figure skater is spinning with angular velocity 20 radians per second. She comes to a stop while making 2 complete turns. Find the average angular acceleration and find the time it took for her to come to rest. Well, just like we did on linear, the first thing to do is to write down the kinematic quantities. Tell me, what's one kinematic quantity that I know? So I want to raise a hand so I can call on you. What's one thing I know in this problem? Between omega naught, omega, alpha, t, and theta, what do I know? Yes, Sean, tell us.
Omega.
Sure. Omega naught or omega?
Omega naught.
Okay, great. Omega naught. What is omega naught?
20 radians.
Good, 20 radians per second. Someone else tell me, what's another kinematic quantity I know? Yes, just. Sure, omega, the final omega. What's omega?
0.
Yeah, because they say she comes to a stop. What else do I know?
Theta.
Yeah, I know theta, the angular displacement. I know theta. They tell me that she went 2 revolutions, 2 complete turn. But tell me, do I get to use revolutions in this equation if my omega is in radians per second? Yeah, no way. No, if omega was in revolutions per second, I could. But if omega is in radians per second, someone's going to have to get converted. And I think I'll convert this guy to radians. So I got 2 pi radians in 1 revolution. So I end up with 4 pi radians. Okay? and they want to know alpha. So hey, you tell me, which of these guys am I going to use? Yeah, the last one. And if it helps you, you know, you can always do this in your head. You can always go, well, that's kind of analogous to V naught, and that's analogous to V, and that's analogous to X, and that's analogous to A. And then you just remember which one you would use for those guys, and then convert it to the rotational form, if that helps you, whatever helps you to do this. But anyway, I got omega squared equals omega naught squared plus 2 alpha theta. So I got 0 squared equals 20 squared plus 2 times alpha times, what is that, 4 pi. And so I get alpha equaling, I think it was like 1.57. 400 divided by 8, oh, I don't know what it is. I'm trying to remember from when I did this yesterday. So I got 400 divided by 8 divided by pi. Oh, 15.9. Okay, and it's negative 15.9 radians per second squared. It's negative because it's going to be a deceleration because I started with an angular velocity and ended with 0. Also, you know, you'll notice I did it without units, but I could have done it with units as well. 20 radians per second squared plus 2 times alpha times 4 pi radians. And then if I take my radians squared over second squared and divide out the radians, I get radians per second squared. Are you guys confident that you can do a problem like this?
Yes.
Alrighty, I heard one yes, and that's good enough for me. So I'm going to look at number 19. Here comes number 19 on your homework. An airliner arrives at the terminal and the pilot shuts off the engines. The initial angular velocity of the fan blades is 1800 radians per second. Okay. And it takes 120 seconds for them to come to rest. What is the angular displacement? Well, which of those 4 kinematic equations are you going to use?
A second.
Well, you can't use 3 because you don't know the alpha. Yes. Yeah, I would use 2. And in fact, you know, just as x equals average velocity times time, theta is going to equal average angular velocity times time. So if it starts at 1800 and ends at 0, what's the average velocity? 900, right? 900 radians per second for 120 seconds. That's 108,000 radians. See what I mean? I mean, this is pretty easy. Theta equals average omega times time. Theta is going to equal 900 radians per second times 120 seconds. So that's all there is to number 19. 13 of you asked for number 19, but is that okay with you? All right. Then, you know what, at this point, I think we'll shut off the camera. So here, wait just a second. Bye-bye.